Hey guys, so this is for Unit 4.6. That's the review unit, and this is homework 2 on it. So we have this funky pipe that has these strange angles in it, and it's bracketed to the wall here on the ZY plane. And so we've got, what it wants us to do is figure out how much weight we can hang here at point D before the pipe starts to rotate about point A, about AB, about the AB axis. So what we're not worrying about is the pipe sliding out because of the force or anything like that. All we care about is the twisting or the moment arm. And it says that it can resist 250 Newton meters worth of moment about it. So looking at it, it's kind of a confusing looking problem because of the different angles and things. But if you step back for a minute and think of a simpler situation, then that helped me to be able to understand what was going on. So I stepped back and said, okay, what if I just imagined just the same bracketed pipe, but it's just a T shape. It's just AB, and if it's lying flat along the y-axis and it has one simple moment arm that's coming straight off it, that's perpendicular to AB, and then I hang a weight straight off of that. That would be a pretty easy situation to figure out, right? I could just set up my moment equation and then solve uh, for the weight, as long as I knew the length of the moment arm, right? And so those same principles are also key here. We need to find a moment arm. We need to figure out what the moment arm is and make sure that it's perpendicular to AB. And then we also need to figure out how long that moment arm is. And then we can set up our moment equation, and it's going to be pretty easy to go from there. So we were given all these things. We were given all these lengths and angles. We're given this angle here, phi, and this angle, theta, and all these different lengths. So to get started on this, at first I was just kind of curious. So I took a second, and I know that doesn't necessarily sound efficient, and you're trying to be efficient with your homework and get it done quickly. But I was just curious, and I think that's a good thing to do sometimes, is just be curious. Allow yourself the freedom to explore the problem a little bit and play around with it. And you'll often discover things that will be helpful to you, which I actually did. So I was curious about what angle AB made with Y. I was like, what angle is that? It gives me LY and LZ, so I know I can figure it out. And I called it angle ABY. And to find that in Mathematica, to set that up, obviously you're going to use arctangent or inverse tangent, and that's LZ, so opposite over adjacent. And then to give it to me in degrees, I had to put slash degree here, and then put the whole thing inside brackets and put n on it. And I believe that the n makes it give it to you in decimal form instead of some yucky fraction that doesn't mean anything to me. So found that, and then I was curious about point C too. I was like, well, where would point C be in XY coordinates? Because I know the length LBC. So I went through and said CX and CY and just used cosine and sine, again using the degree keyword in there, multiplying by that length LBC, that hypotenuse, and slash slash n gives it to me in a decimal form instead of a fraction. So when I got to that point, and I'll post this notebook so you guys can read through these comments more if you want to, but I got to that point and it kind of hit me what I could do for my moment arm. I was looking at it, and I started thinking about it in 2D instead of in 3D. I started looking at it from different 2D angles, and to kind of try and show you what I was thinking, I tried to sketch it out here. So instead of just looking at it and trying to think, well, where's the moment arm and where's it going to intersect at a right angle with AB from W, from point D, I thought, okay, well, I can think about it if I'm just looking at the ZY plane, and if I only look at what's on the ZY plane. So AB is right there, and we found that angle, and so that could be interesting a little bit later. I also have the XY plane here, and if I look down on that, then I can ignore for a minute this theta that makes things more complicated, and I can see that from point B to point C is one angle, that's angle phi, and I can also see that CD goes on from there, and and it's actually not CD, it's C and then whatever this point is. I called it point G over here in my Mathematica notebook, and that projects straight onto the x-axis over this way. And that was interesting. Looking at these two, I thought, hey, wait a second, the x-axis is perpendicular to AB. even though it's not on the XY plane or the XZ plane or something like that, it is 90 degrees apart. If I were to create a plane that included points B and A and any point along the x-axis, then the x-axis is perpendicular to AB. That could be my moment arm. Well, how could I get that to work? I could project the weight, because the weight is going straight up and down in the z-axis direction, right? So if I were to project it over here, and the weight could be over here, right? If I were to take it along this gray line from point D or point G or whatever we want to call it onto the x-axis, then it's still going straight down, and it's on this moment arm now that's perpendicular with AB. But some of you might be saying, but it's not perpendicular to the moment arm. The force or the weight is not perpendicular to the moment arm and to AB, and that's correct. So what I had to do was this part where I said, okay, if I'm assuming that my moment arm is along the x-axis and it's this length from B over to where I've projected from point D, so from B, this turquoise part plus this little black line right here, then what I can do is I can say, all right, my weight, and you can all be amazed at my paint skills, they're great, I know. The weight is still going straight down in the z direction, right? But the component of that weight that I care about is perpendicular to AB. That's what this part is, and that forms a right triangle, correct? Because I have a component of it that's going this way, that's parallel to AB, and a component that's going perpendicular to AB, and the true force is going straight down. So since I know this angle up here, I also know this angle in here. And when I know that, and I know the value of the weight, which I don't, but we can solve for that, then I will know the component of the weight that is perpendicular to the moment arm, and that's what I care about. So what I was able to do once I had that figured out was come over and say, all right, CG, which is, let me zoom out over here, CG, which is really just this distance from C along this part to right under point D, is cosine of theta in degrees, not in radians, times LCD. And that gives it to me there. And then from B all the way out to G, or under D, is going to be LBC plus CG, we just found. And then GX is this part over here that we were talking about, from B out to this gray line. That's what I called GX. And that's going to be cosine of phi times BG, this big triangle. And then I was able to set up that moment arm equation that we talked about in the very beginning. So I took cosine of phi, so the moment arm, I got the moment arm, doing cosine of phi times LBC plus CG, the hypotenuse, times the cosine, and this is now multiplying it by the weight. So a moment is the force times the distance, right? So we got the distance here with our moment arm, and then this is the force we're going to have right here, this cosine times the angle times the weight. And the reason that's the force is because that's where we're finding this perpendicular component of the weight, the portion of the weight that is perpendicular to our axis, to AB. That's what this part is. Cosine of ABY times W gives me this arrow, this side of the green arrow right there, the green triangle. And the way that I tell Mathematica solve for that is I say solve, square bracket, and then I put all my stuff in, my equation, double equal sign. And we know that it can withstand a 250 Newton meter moment. I tell it to solve for W, and this part tells it to give it to me in a decimal, not in some funky fraction. Shift enter to solve it, and I get 96.3105. Oops. It's gone too long. And as you'll notice, that's the correct answer. So we were able to project the force onto the x-axis, which we use as our moment arm, find the length of the moment arm, find the component of the weight that's going perpendicular to the axis AB, and we were good to go.